Welcome to Lecture 2 on Dynamic Corporate Transformation, Volume 2, Enterprise Optimization and Applications. Volume 1 was a representation argument. The enterprise as a point in a declared state space, transformations as a monoid, four architectures assembled under compatibility conditions into a unified object, and the whole thing converging on the general enterprise optimization problem, subject to unified dynamics, admissibility, and the 5 constraint blocks. We had capital floors as one of the constraints, performance targets, risk ceilings, governance identities, and finally, sustainability floors. Plus, the enterprise state vector x of k in the feasible or admissible enterprise state region omega. Now, Volume 2 is about what happens when you actually try to solve that. So we have this Hamilton-Jacobi Bellman HJB equation over here, and this is for a deterministic continuous time control problem. So y, you can see y over here, y is the current enterprise state vector, u is the admissible management control or management decision, s is time, and then this function L of y, u, and s is the instantaneous payoff, reward, or value flow generated by taking control u in state y at time s. V of y and s is the optimal value function over here. And this with respect to the state vector y. Now, the function f to the right, this is the state transition dynamics. Okay, y dot is the evolution, and the gradient v is the instantaneous change in future enterprise value caused by the control-induced movement of the state. So the max of u, which is an element of big U set, is basically where management chooses the admissible control that maximizes the sum of the current payoff and the induced change in continuation value. So at every state and time, the optimal control is U star, which maximizes immediate value plus the rate at which the decision changes the enterprise's future value. Okay? All right. Now, equation at the bottom over here. Now, this is the general enterprise optimization problem, or GEOP objective. So this is the discrete time general enterprise optimization problem, which chooses an admissible enterprise policy pi. Okay, so admissible enterprise policy is pi. Let me just bring this. Okay, over here. That's the pi. And the capital pi is the set of feasible state contingent decision rules. So pi of k is the control prescribed by the policy at period k when the enterprise is in state x of k over here. U of k is the management decision or control at period k, and x of k is the enterprise state vector at period k. Capital K over here, capital K is the terminal period of the planning horizon. And this equation over here, L, is the period K payoff, value contribution, or transformation reward. And the final element here, big phi of, okay, so this is the terminal value. Now this is subject to the constraints in the next period, x sub k plus 1. This represents as the enterprise evolves from the current state t to the next state, current state k and the next state k plus 1, according to its dynamics, the policy selected decision and external uncertainty comes into play. And you can see the expectation operator here as well. So GOP basically is choosing, in this case, pi star that maximizes expected cumulative enterprise value plus the terminal value over here, subject to the enterprise's dynamic state transition law represented over here. Now, I want to frame volume 2 as a ladder of concessions. So each chapter, as we'll go through it, each chapter buys tractability by conceding something. And let us be explicit at each rung about what is being given up. Convexity buys global optimality and costs realism. Linear quadratic structure buys closed form feedback and costs the constraint blocks. Dynamic programming buys the Bellman recursion and costs dimension. Robustness buys distribution-free guarantees and costs sharpness. So the intellectual content of volume 2 is not any single technique. Every one of them is classical. It's really the map of which concession you should make for which enterprise problem and what each one costs you. So if you look at this table, we summarize this dynamic. This says that every optimization method gains tractability by imposing assumptions or accepting limitations. So convex optimization, for example, buys a global optimum, but at the cost of assuming a convex structure, which rules out many increasing returns or non-convex enterprise effects. Nonlinear KKT methods buy local optimality conditions and sensitivity analysis, but constraint qualifications can fail precisely in distressed or degenerate situations. Pontryagin maximum principle gives a costate or shadow price for each state variable, but is fundamentally an open loop framework, and global sufficiency usually needs concavity. Dynamic programming gives true state contingent feedback policies, but suffers from the curse of dimensionality. HJB plus verification can certify an optimal policy without searching over all policies directly, but requires solving a high-dimensional partial differential equation, PDE, that is rarely available exactly. Distributionally robust optimization protects against uncertainty in the probability law itself, but can become conservative and depends materially on the choice of ambiguity radius epsilon. Each rung of the optimization ladder gives a stronger computational or certification benefit, but every gain is purchased with assumptions, dimensionality costs, or conservatism. So let's have a look at this equation at the bottom. So nested optimization problem classes. This says that the optimization classes are progressively more general. So you've got linear quadratic problems that are a special case of convex enterprise optimization over here. Now that is a special case of nonlinear enterprise optimization over here, which sits inside the dynamic enterprise optimization, which in turn sits inside the full GOP, the general enterprise optimization problem. Each successive framework can represent everything in the earlier one, plus more complex enterprise behavior. Now, value can only improve as the admissible problem class expands. So you can see on the right, V of P sub LQ going over to P sub GOP Here, V of P is the best attainable objective value within a given problem class. Because GEOP allows the broadest set of admissible policies and structures, its optimum cannot be worse than the optimum obtained from a more restrictive subclass. Greater modeling flexibility weakly increases the attainable enterprise optimum. Now, the shape of the difficulty. Let's start with the enterprise optimization, chapter 1, and GEOP, chapter 2. So the first two chapters will restate the problem in computational form. Theorem 1.1, enterprise optimization representation theorem. Any declared and internally consistent enterprise decision problem can be represented faithfully and canonically as a constrained optimization problem, preserving exactly the original feasible decisions and preference ordering. Theorem 1.3 characterizes the decision space. Enterprise decision spaces combine continuous, discrete, and policy choices. Discrete decisions destroy convexity and create exponential computational growth, while policy choices can make the problem function valued and potentially infinite dimensional. Theorem 1.4 maps objectives. The enterprise objective is a well-defined function of decisions, inherits the model's regularity for optimization, preserves the optimal set under monotone rescaling or bijective reparameterization, but can change materially when weights, normalization, or aggregation rules change. Theorem 2.1 gives the structure of the feasible region. The GEOP's feasible region is a closed set determined entirely by the dynamics, admissibility, boundary, and constraint structure. It is convex only under corresponding convexity conditions, and whether it is empty is a consistency question independent of the objective. Theorem 2.2, policy existence. If the feasible policy set is non-empty and compact, and the objective is continuous, then an optimal enterprise policy exists and attains a finite maximum value. Theorem 2.3, constraint consistency. GEOP feasibility is determined by joint constraint consistency. When infeasible, the conflict can be localized to a minimal inconsistent constraint set, and in dynamic problems to the first period in which no feasible continuation remains. Theorem 2.4, objective equivalence. When two apparently different objective declarations induce the same preference order over trajectories, Bolza, Meyer, and Lagrange objective forms are mathematically equivalent representations of the same GEOP. So switching among them changes only formulation convenience, not the feasible policies or the optimal solution. Theorem 2.5 is the unified enterprise optimization theorem in computational form, and it is the bridge. The GEOP, as posed in Volume 1, is exhibited as an instance of a class for which Volume 2 supplies solvers. For a certified GEOP, an optimal policy exists, satisfies the appropriate optimality conditions, assigns shadow prices to binding constraints, varies stably with small changes in declared data, and these properties hold independently of the particular solver used. So the GEOP is simultaneously constrained, dynamic, stochastic, multi-objective, and posed over a policy class rather than a decision vector. Volume 2 does not pretend to solve them jointly in general. It solves them jointly under structure and separately in generality. So let's have a look at this illustration. The slide says that the full DCT optimization problem is difficult because it combines 5 problem classes, as represented here, that are each already mature research fields in their own right. So constraint the enterprise must satisfy the 5 declared constraint blocks and remain inside the feasible region sigma. Dynamic, the object being optimized is a trajectory through time, not a single static point. Stochastic, uncertainty enters through both continuous diffusion and discrete jumps. Multi-objective, there is generally a Pareto frontier of efficient trade-offs, not one universally best scalar maximum. Over policies, the decision variable is a policy pi, in capital Pi, a state contingent rule rather than a single finite dimensional control over U in m-dimensional real space. Geob then sits at the intersection of constrained, dynamic, stochastic, multi-objective, policy-based optimization. So let's have a look at the equation at the bottom over here. The policy class, capital Pi, maps X to U measurable. This says an enterprise policy, Pi, is a measurable rule that maps each possible enterprise state X into a management action U. A policy tells management what action to take in every possible state of the enterprise. Why the full policy space is infinite dimensional. So you can see it's infinite dimensional. If the state space is continuous, then a policy is a function that's defined over infinitely many possible states. So choosing an optimal policy is generally an infinite dimensional optimization problem, not simply choosing a finite vector of numbers. And the number of tabular policies is u to the power x, which means if both the state space and the action space are finite, a tabular policy assigns one action to every state. With u possible actions over each of x possible states, the total number of possible policies is u to the power x. Even in a finite tabular setting, the number of possible enterprise policies grows exponentially with the number of states. In continuous settings, the policy problem becomes infinite dimensional. Now, Chapter 3 talks about convex enterprise optimization. Chapter 3 asks, when is the enterprise problem convex? And what do you get if it is? Theorem 3.1, global optimality. In a convex enterprise optimization problem, every local optimum is global. The optimal set is convex, and strict convexity makes the optimum unique. Theorem 3.2 characterizes when the declared feasible region is convex. Essentially, concave inequality constraints and affine equalities. The enterprise feasible region is convex when each constraint block is convex or affine, and this convexity can be certified block by block. Any non-convex block can destroy the guarantee. Theorem 3.3 is about the supporting hyperplane. Every boundary point of a convex feasible set has a supporting hyperplane, providing a linear separator that locally characterizes the feasible region. Theorem 3.4, strong duality under Slater. Now, Slater's condition is a regularity condition for convex optimization that says there must exist at least one strictly feasible point. Under Slater's condition and the stated linear independence condition, the convex enterprise optimization problem has zero duality gap and the dual optimum is attained. Theorem 3.5, the Karush-Kuhn-Tucker KKT in a convex case. In a convex enterprise optimization problem, the KKT conditions characterize global optimality, Under Slater, they are necessary as well as sufficient, and the associated multipliers measure the shadow prices of relaxing constraints. Theorem 3.6. The convex enterprise reformulation theorem, which is the practically useful one. Conditions under which a non-convex looking enterprise declaration admits a convex reformulation, geometric programming, and second-order cone structure hiding inside ratio and product constraints. Many enterprise objectives and constraints can be transformed exactly into equivalent convex forms, such as epigraph, auxiliary variable, monotone, and Gaussian chance constraint formulations, while preserving the original solution. So let's have a look at these charts over here. This shows the trade-off between convexity and realism. The left surface is convex or concave enough that any local optimum is also the global optimum. So standard convex methods give strong guarantees. The surface on the right basically introduces realistic enterprise effects, such as thresholds, increasing returns, and network interactions. These create multiple peaks, as you can see over here, then over here, then over here. So it's creating multiple peaks and valleys, so a local optimum may no longer be globally best. So convexity turns local optimality into global optimality, but realistic thresholds and network effects often destroy convexity and therefore weaken those guarantees. Let's have a look at the equation at the bottom here. Convex enterprise optimization problems, in this case, we are minimizing f of x over x subject to g sub I, which is negative, g sub I of x being negative, and ax equals b. So we choose the decision vector x to minimize the objective over here, which is the f of x, while satisfying inequality constraints g and linear equality constraints ax equals b. Find the best feasible enterprise decision subject to all declared limits and requirements. First order condition for global optimality, you see the gradient f of x star. X minus x star is positive for all x which is in sigma. So for every x, now let's talk about x star over here. That's the optimum. So x star is the optimal solution and sigma is the feasible region. The inequality says that from x star, moving toward any other feasible point cannot reduce the objective. So at the convex optimum, there is no feasible direction that improves the objective. Everywhere it's going, gradient is going down. For a convex enterprise problem, this first order condition is enough to certify global optimality, not merely local optimality. At the optimum, the KKT conditions give multipliers on the inequality blocks, and those blocks are not arbitrary. They are from volume 1, the capital floors, the performance targets, the risk ceilings, the sustainability floors. So the multiplier on the risk ceiling is the marginal enterprise value of one additional unit of risk appetite. The multiplier on the capital floor is the marginal cost of the capital adequacy constraint. Similarly, the multiplier on the sustainability floor is the shadow price of the firm's ESG commitment in the firm's own objective units. So under a convex declaration, they are computed, and complementary slackness tells you which ones are actually binding. My experience is that most declared constraints are slack, and the discovery of which 3 of 30 are binding is worth more than the optimum itself. The concession, of course, is that convexity is a strong assumption about an enterprise. Increasing returns, network effects, threshold effects in adoption, and fixed costs all break this convexity assumption. So we can look at this chart over here. It illustrates complementary slackness and shadow prices across 8 different enterprise constraints. The bars show each constraint's multiplier, lambda, which is the marginal value of relaxing that particular constraint. So the risk ceiling has the highest shadow price, 4.8. As you can see, risk ceiling is 4.8, followed by capital floor at 3.1. So those are the most economically restrictive constraints. Then you have sustainability, performance, and over here performance and time. These 3 also bind, but at lower marginal values. The constraints labeled slack here, governance, identity, and budget, and legal as well, they have a lambda of 0, meaning relaxing them would add no value because they are not currently limiting the optimum. So binding constraints have positive shadow prices that quantify what they are costing the enterprise, while slack constraints have 0 shadow price and cost nothing at the margin. So we look at this lambda risk, the dual function, and it is obtained by okay, no, that's the lambda risk. Okay, so here this equation, g is the dual function, and g of lambda and v, it is obtained by minimizing the Lagrangian over the primal decision variable, which is x. It's concave in the multipliers lambda and v. The dual problem asks what bound on the original optimization problem is implied by a given set of constraint prices. So weak and strong duality, we see that D star is less than P star over here, and under Slater's condition, in fact, D star is equal to P star. So P star is the optimal value of the original or primal problem, and D star is the optimal value of the dual problem. Weak duality says that the dual cannot exceed the primal optimum. Under Slater's condition, the gap disappears completely. With the appropriate regularity condition, the constraint price formulation recovers exactly the same optimal value as the original problem. And finally, we look at the sensitivity of the optimum to constraint limits. You see the gradient P star equals minus lambda star. This says that the optimal Lagrange multipliers measure how the optimal value changes when the constraint limits B are changed. So the optimal multiplier is the shadow price of a constraint, the marginal economic value of relaxing or tightening that constraint. Duality converts constraints into prices, and under strong duality, those prices fully characterize both the optimum and its sensitivity to scarce resources or binding limits. So back to this lambda risk element over here. So this is the shadow price of the enterprise risk constraint. So you've got J star, which is the optimal enterprise value, and you've got R max, which is the maximum allowable risk. So lambda sub risk is the marginal value of relaxing that risk ceiling. Lambda sub risk tells management how much optimal enterprise value would increase if the permitted risk limit were raised slightly. So chapter 4 is about nonlinear enterprise optimization. Theorem 4.1, first order necessary conditions. At any local optimum, the objective cannot improve along any feasible direction. At an interior optimum, the gradient is 0, but this first order condition alone does not guarantee optimality. Theorem 4.2, second order sufficient conditions. Positive definiteness of the Hessian of the Lagrangian on the critical cone. If a KKT point has positive curvature of the Lagrangian along every critical feasible direction, then it is a strict local optimum with quadratic growth around that point. Theorem 4.3 is KKT in the nonlinear case. Theorem 4.4 is about constraint qualification. So LICQ is the linear independence constraint qualification. Mangasarian, Fromovitz, as well as Slater. Mangasarian, Fromovitz constraint qualification, MFCQ, is a weaker regularity condition than LICQ that ensures that active constraints meet in a sufficiently non-degenerate way for KKT theory to work. So in nonlinear enterprise optimization, every qualified local optimum satisfies the KKT conditions, but KKT alone does not prove optimality unless supported by convexity or appropriate second order conditions. So this is just the basics. Constraint qualification fails, however, when the constraint gradients are degenerate at the optimum, when geometrically the feasible set has a cusp. In enterprise terms, this is the situation where several constraints bind simultaneously and their directions of tightening are linearly dependent. Practically, your capital floor, your covenant, and your rating threshold all bind at once and all move together. This is a firm in distress, and it is exactly the state in which management most wants an optimization answer. So the regime where the enterprise most needs the theory is indeed the regime where the qualification most often fails. Theorem 4.5 gives local stability of the optimum. Under LICQ, second order sufficiency and strict complementarity, a local enterprise optimum is locally stable. Small parameter changes produce a unique nearby optimum, multipliers, and active constraints that vary smoothly with the parameters. Theorem 4.6 is about sensitivity. X moves as parameters move, which is the implicit function machinery and gives the derivative of the optimum with respect to every declared parameter. That derivative is what makes the model useful for governance rather than mere computation. It tells you which parameter estimates your answer actually depends on. So let's have a look at this chart. When several constraints bind simultaneously and their gradients become nearly linearly dependent, the linear independence constraint qualification LICQ can fail. Exactly the kind of degeneracy that often appears when a firm is under severe distress. You see a point like that, gradient is nearly linearly dependent, and LICQ fails at this point. So the equation over here is the KKT stationarity condition together with complementary slackness. So at the candidate optimum, Z star, over here, the gradient of the objective L is exactly balanced by the gradients of the active constraints. The multipliers lambda I correspond to inequality constraints GI, while mu of j correspond to equality constraints h of j. Okay, now lambda I GI over here is equal to 0, and this is complementary slackness. It means that an inequality constraint can carry a positive multiplier only if it's binding. If the constraint has slack, then its multiplier must be 0. At the optimum, there is no feasible direction that improves the objective, and only the constraints that are actually binding have a positive shadow price. Okay, now let's move to the equation at the bottom. Now, the tangent cone of feasible directions. So This describes the directions D in which you can move locally from X star without immediately violating any active inequality constraint. The tangent cone is the set of locally feasible directions available to the enterprise at the current constraint point. The MFCQ, the Mangasarian-Fromovitz constraint qualification over here, there exists D such that for gradients G sub I, for all active inequality constraints, while the equality constraint gradients are linearly independent, there must exist at least one direction that moves strictly away from every active inequality boundary while remaining compatible with the equality structure. So MFCQ ensures that the constraints meet cleanly enough for the KKT multiplier system to behave properly rather than being degenerate. The first expression identifies the feasible local directions. MFCQ ensures there is enough local freedom for standard first order optimality conditions to be valid. Okay, so now we move to dynamic enterprise optimization. Theorem 5.1 is about trajectory existence. Under standard continuity, Lipschitz, and growth conditions, every admissible decision path and initial state generates a unique enterprise trajectory over the planning horizon. Theorem 5.2, enterprise state evolution. Enterprise trajectories depend continuously on both the initial state and the model dynamics, while under stable contracting dynamics, differences in initial conditions decay exponentially over time. Theorem 5.3, admissible policies. An admissible enterprise policy set is non-empty when a feasible reference policy exists, can be safely concatenated across review points, and is convex only under suitably affine dynamics and convex constraints, generally not under nonlinear dynamics. Theorem 5.4, dynamic feasibility, which is where recursive feasibility from volume 1 becomes an optimization constraint rather than an analytical property. So under compact controls and continuous constraints, feasible enterprise trajectories are uniformly bounded and equicontinuous with convex velocity sets. The feasible trajectory set is compact and a continuous objective therefore attains an optimal dynamic enterprise path. Theorem 5.6 gives the dynamic enterprise optimization equivalence between the trajectory formulation and the policy formulation. Dynamic enterprise optimization can be reformulated equivalently between Bolza, Meyer, Lagrange, and autonomous forms, while discretizing decisions on a time mesh produces a finite dimensional nonlinear optimization problem whose optimum gives a valid lower bound on the full dynamic problem. So let's have a look at this chart. Recursive feasibility is a property of the policy. A state may be feasible today, yet a poor policy can still steer the enterprise toward an unavoidable future exit from the feasible region. As you can see, exit is already determined over here. So the equation at the bottom, this equation is basically, it says that every admissible enterprise trajectory is Lipschitz continuous in time. Now, the state cannot change arbitrarily fast. Its rate of movement is uniformly bounded by m over here. As a result, t over here, you see this t sub ad of x sub 0 implies t sub ad x sub 0 is in C in Rn, meaning every admissible trajectory belongs to the space of continuous paths from the time interval 0 to t, which is represented over here, into the enterprise state space Rn. Feasible enterprise trajectories evolve continuously at a bounded speed, which gives the trajectory set the compactness structure needed for existence results in dynamic optimization. Chapter 6: Optimal Control of Enterprise Systems. Theorem 6.1: The Pontryagin Maximum Principle, PMP, for enterprise systems. The proof in the text is the classical needle variation argument. Perturb the control on an interval of length epsilon around a Lebesgue point, propagate the first order trajectory response, and use optimality. Theorem 6.3 gives costate evolution. The costate is uniquely determined backward from the terminal condition and aggregates the future marginal value of the current enterprise state, weighted by the linearized straight transition dynamics. Theorem 6.4, transversality. The terminal costate is determined by the terminal objective and any endpoint constraints, and if the ending time is itself a decision, optimality requires the total marginal value rate at termination to be 0. Theorem 6.5, optimal enterprise trajectory theorem, Mangasarian sufficiency. The concavity condition under which the necessary conditions become sufficient. If the PMP conditions hold and the Hamiltonian and terminal objectives are concave, then the resulting enterprise control and trajectory are globally optimal. Strict concavity in the state makes the optimal trajectory unique. Theorem 6.6, enterprise feedback control representation. The LQ synthesis with the Riccati equation and closed form feedback in a linear quadratic enterprise problem, the Riccati equation generates a globally optimal state feedback policy, converting future state costs into a real-time control value. So let's have a look at the first equation over here. The Hamiltonian, the immediate payoff L over here, plus the costate lambda right here, dotted into the direction the state is about to move. The second equation, the adjoint equation, it runs backward from the terminal condition. The costate today is determined by the future it enables, integrated backward. A capability with 0 terminal value entering the dynamics of nothing valuable has costate identically 0. The third equation is over here. That is the maximum condition. At every instant, the optimal decision is whichever admissible choice maximizes the Hamiltonian right there, given the prevailing costate. Note what this is not. It is not a schedule chosen at the outset and then executed. It is a rule evaluated moment by moment against prices that are themselves evolving backward from the horizon, which is why the forward and backward equations must be solved together. So now we want to look at the chart. Now here you got the top panel, which shows the enterprise state evolving forward in time under the optimal control, while the bottom panel it shows the costate evolving backward from the terminal condition, and where each costate lambda is the shadow value of improving the corresponding state variable at each point in time. So the Hamiltonian conservation that's being displayed over here has no explicit time dependence. So when you have h as a constant, so no explicit time dependence. So along an optimal enterprise trajectory, an autonomous Hamiltonian remains constant over time. Now you have the terminal transversality condition, lambda of capital T, which is the terminal costate, and the gradient phi. So that is the sort of the terminal enterprise value, okay? And T sub x of big T, M, is the tangent space to the terminal constraint manifold. So at the endpoint, the difference between the costate and the terminal value gradient must be orthogonal to every feasible direction along the terminal constraint surface. Here is the interpretive point I want to leave you with, and it is the reason PMP belongs in an enterprise theory at all. The costate lambda of T is the shadow price of the enterprise state. Lambda I is the marginal value at time t of an extra unit of state variable I, an extra unit of human capital, an extra point of customer sentiment, an extra unit of installed capability. And the adjoint equation runs backward from the terminal condition, so the present value of a capability is determined by the future it enables, integrated backward. A capability whose terminal value is 0 and which does not enter the dynamics of anything valuable has costate identically 0, and the maximum principal will spend nothing on it correctly. I think this is the most economically literate object in either volume, and it deserves to be better known outside control theory. Enterprises routinely fund capabilities with 0 costate. Let's have a look at this Riccati equation over here, which is also represented at the bottom as well. And so the Riccati equation integrated backwards from the terminal weight Qt together with the feedback law it produces. And this chart says that each capability has a costate or shadow price measuring the marginal contribution to future enterprise value. Capabilities such as the data platform have a high costate and should receive more funding, while a capability like legacy migration has a near 0 costate because it adds essentially no incremental value along the optimal trajectory. So the Riccati equation determines the matrix P of T, so we have, let's see, the matrix P, yeah. So this equation determines the matrix P of T that encodes the future cost of being away from the desired enterprise state. Starting from the terminal penalty Q sub big T, or capital T, it is solved backward through time and determines the optimal feedback rule. Now, the optimal value decomposition, the J of U equation over here, says that the cost of any policy equals the minimum achievable cost, represented by this first term, plus a non-negativity penalty measuring how far the chosen control U, that's over here, deviates from the optimal feedback control. Since the second term is minimized at 0, U star, as you can see U over here, U star, the Riccati equation computes the optimal feedback law, and then this second equation proves that any deviation from that law can only increase the enterprise objective cost. So now we move on to dynamic programming for enterprise systems, chapter 7. Theorem 7.1 is the Bellman's principle of optimality. If a decision sequence is optimal for the full enterprise problem, then from any intermediate state onwards, its remaining decisions are also optimal for the corresponding continuation problem. Theorem 7.2 gives the Bellman equation. The Bellman recursion exactly characterizes the finite horizon value function, and a policy is optimal from every state precisely when it chooses a stage-wise maximizing action at each step. Theorem 7.3, enterprise value function existence theorem. Now, existence of the value function via the Banach fixed point on the Bellman operator, which is a beta contraction in sup norm. Because the Bellman operator is a contraction, the infinite horizon enterprise value function exists uniquely as its fixed point. Theorem 7.4, value iteration convergence. Value iteration converges geometrically to the unique optimal value function, provides a computable stopping error bound, and guarantees that policies based on an approximately correct value function are themselves near optimal. Long horizon enterprise problems are precisely the ones where value function error is most amplified into policy error. Theorem 7.5 gives policy iteration convergence, finitely many iterations on finite spaces, and monotone improvement. Policy iteration improves enterprise policy value monotonically, strictly improves whenever the current policy is suboptimal, and on finite state action spaces reaches an optimal policy after finitely many iterations. So now we have this Bellman's equation represented over here. The value of standing at x is the best you can do this period. And then you have L of x and u plus the discounted expected value of whatever that decision, wherever that decision takes you. One line, recursive, and it characterizes the finite horizon value function exactly. No approximation has entered yet. A policy is optimal from every state precisely when it takes a maximizing action at each step. And then we have a computable stopping rule, which is what makes the value iteration usable rather than merely convergent, represented over here. The distance from the true value function is bounded by the change over the last iteration, inflated by beta over 1 minus beta. Finally, we have the third equation in this area. So act greedily on a value function accurate to epsilon, and the policy you get loses at most 2 beta epsilon over 1 minus beta, represented here. Now, this chart shows that the discount factor beta approaches 1. Small value function errors are amplified much more strongly into policy error, and value iteration converges much more slowly. So long horizon enterprise problems are substantially harder to solve accurately. That's pretty intuitive as well. Now this equation at the bottom, this means the Bellman operator is a contraction mapping under the soup norm. Therefore, the Banach fixed point theorem, it has a unique fixed point. V star equals TV, and it is unique. The final bound, represented over here, it says that if the value function used to construct the policy is within epsilon of V star, the resulting greedy policy is also provably close to optimal. Because the Bellman operator is a contraction, the Banach fixed point theorem guarantees a unique optimal value function, and geometric convergence to it, approximate value functions also produce policies with a bounded loss from optimality. The 8JB enterprise framework in Chapter 8, Theorem 8.1, the 8JB equation. If the enterprise value function is smooth, it satisfies the 8JB equation, so the optimal policy is obtained by maximizing the instantaneous reward plus the value of the induced state evolution at each point in time. Theorem 8.2, the verification theorem. Any smooth function that satisfies the 8JB equation provides an upper bound on value, and if an admissible control attains the 8JB maximum along its trajectory, that control is certified optimal, and the candidate function is the true value function. Now, 8JB is necessary. If the value function is C1, it solves the PDE. Verification is sufficient. If you find any W in C1 solving HJB with the right terminal data, and if an admissible control attains the 8JB maximum along its own trajectory, then that control is optimal and W equals V. Theorem 8.3 gives the optimal feedback. If an optimal feedback law generates a well-defined closed-loop trajectory, then that feedback law is optimal from every reachable state, and every resulting closed-loop trajectory is itself optimal. Theorem 8.4, value function characterization. If the enterprise value function is sufficiently smooth, it is uniquely characterized as the solution of the HJB equation with the correct terminal condition. Theorem 8.5, the continuous time Bellman principle. The continuous time Bellman principle uniquely characterizes the enterprise value function, and when the value function is smooth, the Bellman identities are equivalent to the HJB equation. Theorem 8.6, optimal enterprise policy representation. An enterprise control is optimal exactly when it follows the Hamiltonian maximizing feedback law, and along an optimal trajectory, the Pontryagin costate equals the gradient of the value function, linking PMP to HJB as two representations of the same optimal. Now, HJB is a PDE on the enterprise state space. For n equals 20, a modest enterprise declaration, grid-based solutions is out of the question, and even modern deep BSDE methods are strained. The framework's answer is structure. Linear quadratic reductions, where the declaration permits decomposition along the dependency graph of volume 1, the function approximation. But it should be recognized that the exact HJB solution of a full enterprise GEOP is not computed. Too many dimensions. What is computed is a structured approximation. So we look at this HJB equation. We have seen it in the opening slide. At each state and instant, maximize the immediate payoff plus the value of the motion that decision induces, with the value function pinned at the horizon by the terminal condition. Now, HJB is necessary. If the value function is smooth, it solves the equation. We discussed that before. And verification is sufficient, and it turns the other way. Find any smooth candidate W solving the equation with the right terminal data, exhibit an admissible control attaining the maximum along its own trajectory, and that control is certified optimal, and W is the value function. You can go that way as well. So now the chart here, this panel shows the value function V of X and T. For every enterprise state X and time T, it gives the maximum future value still attainable from that point. The right panel over here shows the optimal feedback policy derived from the gradient of that value function. The slope gradient V tells us the marginal value of changing the state, and the optimal control uses that information to push the enterprise in the value improving direction. Okay? The value function tells us how valuable each possible future state is, and its gradient tells management what action to take from the current state. Now at the bottom we see this the couple of equations with respect to the viscosity solution characterization of the HJB equation. So we have for all phi in C1. Now, if V minus phi has a local maximum, then you have this particular expression will be negative, and if V minus phi has a local minimum, then this expression will be positive. So that's the viscosity solution characterization. V of xt, so V over here is the value function. Phi is in C1, smooth test function, which is used to probe V locally. And then phi of t, that is the time derivative of the test function. Now we have the gradient or gradient phi, which is the gradient with respect to the state vector x. H over here is the Hamiltonian evaluated at the current state and local gradient. Okay, so we talked about v minus phi having a local maximum means that phi touches v from above, and v minus phi having a local minimum, which means phi touches v from below. The two inequalities define v simultaneously as a viscosity subsolution and supersolution. When both hold, v is a viscosity solution of the minus vt minus h, this expression. And so even when v is not classically differentiable, the HJB equation remains valid in the viscosity sense by testing it against smooth functions that touch v locally from both above and below. Okay, so now I want to talk about Pontryagin and Hamilton-Jacobi as a single optimum. So theorem 6.1, the maximum principle, state equation forward, adjoint equation backward, and each instant the control maximizes the Hamiltonian. The costate is the shadow price of the state, the marginal value of one more unit of human capital, as an example. In the linear quadratic case, the Riccati equation synthesizes those prices into a feedback law. The costate stops being a schedule along one trajectory and becomes a field defined at every state. Theorem 8.6, along an optimal trajectory, the Pontryagin costate equals the gradient of the dynamic programming value function. So the first equation is the Pontryagin maximum principle, and the Hamiltonian H over here combines the current period objective L with the future value of changing the state measured by the costate lambda. The optimal state evolves forward, the costate evolves backward, and the optimal control U star maximizes the Hamiltonian at each instant. The optimal decision balances immediate enterprise value with the shadow value of how that decision changes the future state. Moving down to the Riccati equation over here, which determines P of t, we've covered this already. Once P of t is known, the optimal policy is a linear feedback rule that adjusts the control according to the current state. So the Riccati equation converts the dynamic optimization problem into an explicit optimal feedback policy. And now that takes us to the third equation. Along the optimal trajectory, the Pontryagin costate equals the gradient of the dynamic programming value function. So that's where we see the link between HJB and Pontryagin. This says that along the optimal trajectory, the Pontryagin costate lambda is exactly the gradient of the HJB value function of the state. So Pontryagin shadow price approach and Bellman's value function approach are two representations of the same underlying optimality structure. Okay? All right, now we move to chapter 9, which is stochastic enterprise optimization. Theorem 9.1, existence of stochastic enterprise solutions. Under standard measurability, Lipschitz, growth, and adapted policy conditions, the stochastic enterprise dynamics admit a unique, strong solution with finite second moments over every finite horizon. Theorem 9.2 is the Ito evolution. For a stochastic enterprise diffusion, any smooth function of the state evolves according to Ito's formula, adding a curvature times variance correction term that has no counterpart in the ordinary deterministic chain rule. Theorem 9.3, stochastic dynamic programming. In stochastic enterprise optimization, the value function satisfies the dynamic programming principle along an optimal policy. Accumulated reward plus remaining value forms a martingale, while under any admissible suboptimal policy, it is a super martingale. Theorem 9.4, the stochastic AJB. In stochastic enterprise control, the value function satisfies a stochastic AJB equation in which the deterministic state transport term is replaced by the diffusion generator, so optimal decisions account explicitly for both expected dynamics and uncertainty. The new term is the trace of the diffusion against the Hessian. Theorem 9.5 gives us the Feynman-Kac expectation representation. Under a fixed Markov policy, expected enterprise value can be represented equivalently through the Dynkin-Feynman-Kac, the solution of a linear PDE, linking stochastic expectations and policy value equations exactly. Theorem 9.6 is the optimal stochastic policy. If a smooth candidate solves the stochastic HJB equation and a measurable feedback policy attains its maximizing control, then that policy is optimal and the candidate is the true stochastic enterprise value function. Now, let me make one structural observation. The second order term means the optimal enterprise policy depends on the curvature of the value function, not merely its gradient. Where V is concave, uncertainty is costly and the policy is precautionary. Where convex, uncertainty is valuable and the policy is risk-seeking. Now, real options live in the sign of the second derivative of V. The framework does not need a separate real options chapter because the convexity of the value function is the option value. So we look at this equation at the top. This is the stochastic HJB. So here, everything from the deterministic version survives, plus one new term, which is represented over here. It's the trace of the diffusion matrix against the Hessian of the value function. The optimal policy now depends on the curvature of the value function, not merely on its gradient. So the value function v of xt equals u max, maximizing value that's attainable from state x at time t onward. The value function assigns to every enterprise state x and time t the maximum future value still attainable if management acts optimally from that point onward. So the chart here shows that the left side of it shows a plotting of the value surface v of xt, showing how the value of a state changes with both state and time. The right panel plots the resulting optimal feedback policy over here, and at different points in the horizon. As time changes, the slope of the value function changes, so the optimal action for the same enterprise state also changes. Okay? So here you can see enterprise state, and you can see the convex uncertainty creating value and real options over here. So the concave uncertainty destroying value, as you can see, penalizes the spread. Okay, and then the uncertainty creates value, real options over here. Now, the Feynman-Kac representation linking an expected discounted future value expression to its corresponding backward PDE, this is what we are looking at over here. So U, over here, U is the expected discounted enterprise value when the current state is X at time T. And E is the expectation operator, conditional expectation, given X of T. X sub S is the stochastic enterprise state at future time S. Big T is the terminal condition. And then L is the instantaneous enterprise payoff or value flow under policy pi. R is the discount rate, and you can see the discount factor over here, and phi of xt, that's xt capital T, that's the terminal enterprise value at horizon capital T. And then on the right side, we see u of t, which is the time derivative, dt du, time derivative of the value function. And then L, as we discussed it, L is the infinitesimal, over here, L pi, is the infinitesimal generator of the stochastic enterprise dynamics under policy pi. It captures the effect of drift and diffusion on pi. Okay. And so what we see here is the expected present value of all future enterprise payoffs plus the terminal value is exactly equivalent under the stated stochastic dynamics to solving the backward equation with terminal condition u of x and big T equals phi of big T. Chapter 10, Neurofuzzy Robust Enterprise Optimization. Theorem 10.1, Fuzzy Enterprise Representation. A fuzzy enterprise state can be represented exactly by its nested alpha cut sets, and conversely, any nested left continuous alpha cut family uniquely determines the fuzzy membership function. Theorem 10.2 gives existence of neurofuzzy enterprise policies on a compact state space. Under compactness and continuity conditions, the neurofuzzy enterprise policy optimization problem attains an optimal policy rather than merely approaching a supremum. Theorem 10.3, the Anfis approximation theorem. A universal approximation result. Adaptive network fuzzy inference systems are dense in the continuous functions on compacta. Anfis models are universal approximators on compact enterprise state spaces. Any continuous enterprise decision rule can be approximated arbitrarily closely by a sufficiently rich neurofuzzy system. Theorem 10.4 gives neurofuzzy robustness. A neurofuzzy enterprise policy can guarantee constraint satisfaction for all uncertainty realizations above a chosen possibility threshold, while stronger robustness shrinks the feasible set and typically reduces attainable objective value. Theorem 10.5, convergence of enterprise Anfis or hybrid learning. Under the stated hybrid learning and step size conditions, Anfis training produces a non-increasing convergent loss sequence, and every accumulation point is a stationary point of the reduced learning objective. Theorem 10.6 embeds it back in the GEOP, unified neurofuzzy GEOP theorem. The unified neurofuzzy GEOP attains an optimum, contains deterministic and crisp, robust GEOPs as special cases, and can approximate any continuous enterprise policy arbitrarily closely with correspondingly small loss in satisfaction accuracy. The mathematical content is Stone-Weierstrass flavored, which is a sufficiently rich but simple class of functions that can approximate a much broader class of functions arbitrarily well. Fuzzy rule bases let you encode expert enterprise knowledge. For example, if margin compression is severe and capability maturity is low, then we can say that the transformation intensity should be moderate, in a form that is both differentiable and auditable. It is a mechanism for putting a prior on the policy when the dynamics are not identifiable. Given Volume 1's Theorem 4.5, which was the model validation theorem, that is a coherent response rather than a soft one. Universal approximation theorems say a representation exists. they say nothing about sample complexity, and enterprise data we know is scarce. So the universal approximation result we can see over here, the adaptive network fuzzy inference system, ANFIS, it is dense in the continuous functions on a compact set over here. So any continuous enterprise decision rule can be approximated as closely as you like. So the charts on the left side, it shows fuzzy membership functions for the input margin compression. You can see here margin compression. And so instead of forcing the enterprise into a single crisp category, the model allows partial membership in qualitative states such as low, moderate, and severe. These curves encode, so these curves are therefore encoding the expert judgment as smooth numerical priors. The right panel shows the resulting ANFIS policy surface. Over here, you can see the policy surface as a function of margin compression and capability maturity. So margin compression and capability maturity. Because the fuzzy rules are blended continuously, the recommended policy changes smoothly rather than jumping abruptly at arbitrary thresholds. Now at the bottom, we see the ANFIS output as a weighted combination of fuzzy rules. Okay, so over here. Now this says that the ANFIS prediction y hat of x is formed by combining the outputs of fuzzy rules. So R fuzzy rules, R different fuzzy rules. Each rule produces a local linear output, which is over here, p sub r to the power t x plus q sub r, and that output is weighted by the rule's normalized firing strength, which is w bar sub r. Now, the normalized firing strength of each rule, w bar of r, is basically each rule's weight, and is determined by multiplying the membership grades, which is mu, of the input variables, and then normalizing across all rules so the weights sum to 1. So here you're just normalizing it. Finally, universal approximation result, which is shown over here. The ANFIS function class is dense in CK, the continuous functions on a compact set K. A sufficiently rich ANFIS can approximate any continuous enterprise decision rule on a compact state space arbitrarily closely. We talked about this before. Expert qualitative judgments are converted into smooth fuzzy memberships, and ANFIS combines them into a differentiable enterprise decision surface that varies continuously with the state of the firm. Now we move on to Chapter 11, Distributionally Robust Enterprise Optimization, DRO. Theorem 4.3, Model Validation Theorem. You do not know the distribution, so do not pretend to. Optimize against the worst case over an ambiguity set of distributions. Theorem 11.1, Distributionally Robust Reformulation Theorem. This gives the moment set reformulation. A distributionally robust enterprise problem over uncertain probability laws can be reformulated as a finite dimensional convex optimization problem with strong duality under an interior moment condition, with equality under a Slater condition on the moment vector. The adversarial inner problem becomes a finite dimensional convex program, jointly convex with the outer minimization when f is convex in f of x. An infinite dimensional worst case over measures collapses to finitely many multipliers. So we look at this chart, which over here, which illustrates the logic of distributionally robust optimization. Instead of trusting a single fitted probability distribution, the model considers all distributions that are consistent with the declared moment information and assumes an adversary will choose the one that produces the worst expected outcome, so being pessimistic. The gold line curve is the empirical or nominal distribution, while the surrounding curves represent all these different curves represent alternative probability laws that match the same declared moments. The adversary selects the most damaging admissible law. Okay, so now we want to look at this this equation on the right. This is the dual upper bound for a moment-constrained, distributionally robust optimization problem. We have P. P is a candidate probability distribution for the uncertain variable zeta. P sub MOM is the ambiguity set of all distributions satisfying the declared moment restrictions. And then you've got expectation of F. Okay, expected value of the payoff, loss, or objective, which is F under distribution P. Okay, and F of zeta is the uncertain quantity being evaluated. Okay, psi of zeta is the vector of declared moment functions. So what we are then looking at is a vector of specified moment values, which is M, and then lambda, which in this case lambda, positive lambda, is a vector of dual multipliers or shadow prices associated with the moment constraints. Okay, and then lambda sub 0 is the scalar dual intercept. Now lambda to the power t m is the value assigned by the dual multipliers to the prescribed moments. So the condition, this whole condition, lambda 0 plus lambda to the power t psi zeta, which is greater than or equal to f of zeta, requires the dual function to dominate f of zeta for every admissible realization of zeta. The left-hand side asks for the worst case expectation in terms of value over every probability law that's consistent with the specified moments. The right-hand side replaces the infinite dimensional search, okay, over the probability distributions with a finite dimensional optimization over the multipliers lambda. In compact terms, the worst case expectation under moment uncertainty is bounded above by the cheapest affine combination of the known moments that dominates the uncertain payoff f pointwise. And then we are minimizing over decisions the worst expected loss over here or across every distribution the data cannot reject. The premise is exactly volume 1's validation theorem. You do not know the distribution, so do not pretend to. And on the right, the striking structural fact, the worst case is attained by a law supported on at most k plus 1 points, represented over here. So distributionally robust decision problem X is an element of capital X. It is basically, it says that management chooses the decision X to minimize the worst case expected loss over all probability distributions P in the ambiguity set P. Choose the enterprise decision that performs best against the most adverse probability distribution still considered plausible. So the existence of a worst case distribution over here attaining the supremum, this says that the worst case distribution is not merely approached under the theorem's conditions, it is actually attained by some p star. So if the ambiguity set is defined by k moment constraints, a worst case distribution can be chosen with support on at most k plus 1 points. So even though the ambiguity set may contain infinitely many probability laws, the worst case can be represented by a finite distribution with only a small number of scenarios. Distributionally robust optimization protects against uncertainty in the probability law itself, while the support bound makes the worst case distribution computationally manageable. So DRO protects the enterprise not just against uncertain outcomes, but against uncertainty about the probability distribution itself by optimizing against the worst distribution consistent with the available evidence. Theorem 11.3 is about the Wasserstein duality. Wasserstein duality converts distributional ambiguity into a tractable robustness penalty. For a Lipschitz objective, the worst case expectation over a Wasserstein ball equals the empirical expectation plus ambiguity radius multiplied by Lipschitz sensitivity. The Kantorovich-Rubinstein result says that the Wasserstein distance between two probability distributions P and Q can be understood as the largest possible difference in expected value that the two distributions produce over all functions that are not too sensitive to changes in their input. So if the objective function f is Lipschitz continuous, the sensitivity bounded by L of f, then when we consider all probability distributions lying within a Wasserstein distance epsilon of the empirical distribution P, the worst case expected value is determined by the empirical expectation plus a penalty that depends on the ambiguity radius epsilon and the probability sensitivity L of f. The worst case over an infinite dimensional ball of probability measures is then exactly the empirical average plus the radius times the Lipschitz constant. No optimization, it's in a closed form. Your robust valuation is your sample valuation, penalized by how far you are willing to admit your data might be wrong, multiplied by how sensitive your objective is to the thing you are uncertain about. Theorem 11.6 then gives us finite sample performance guarantees, the out-of-sample bound that justifies the radius choice. The Wasserstein robust enterprise decision comes with a finite sample out-of-sample performance guarantee with confidence 1 minus beta. And under Lipschitz regularity, that guarantee becomes asymptotically exact as the sample size grows. So in the chart, in the left panel, we can see mass on the vertical and zeta on the horizontal. This shows the Wasserstein ambiguity set. Probability mass from the empirical observations can be transported to nearby locations as long as the total transport cost stays within the radius of epsilon. The right panel here, it shows the ambiguity radius on the horizontal axis and the worst case expectation on the vertical. It shows the consequence. The worst case expected value rises linearly with ambiguity radius with scope equal to the Lipschitz constant L of f, so a more sensitive objective pays a larger robustness penalty. The cost of distributional robustness is exactly epsilon L of f, so flatter, less sensitive enterprise objectives are cheaper to make robust. Now, this equation over here shows the worst case over an infinite dimensional ball of probability measures equals the empirical average plus the radius times the Lipschitz constant. Your robust valuation, as we discussed, is your sample valuation. Distributional uncertainty adds that penalty we discussed. Excuse me. Now, the bottom equation over here, it's the finite dimensional dual representation. This rewrites the infinite dimensional search over all probability distributions as an optimization over a single multiplier kappa. So together with one worst case perturbation problem around each observed data point zeta of I over here. Instead of searching over infinitely many distributions, Wasserstein duality reduces the problem to a finite optimization that prices how far probability mass can move away from the observed data. Wasserstein robustness converts uncertainty about the probability law into a transparent penalty for both the size of the ambiguity set and the sensitivity of the enterprise objective. Theorem 11.3, the Kantorovich-Rubinstein theory. The transport distance between two laws is the largest difference in expectation they can produce across all functions that are not too sensitive to their input. The worst case over an infinite dimensional ball of probability measures equals the empirical average plus the radius times the Lipschitz constant, as we've discussed. So the first equation over here is the Kantorovich-Rubinstein duality, the Wasserstein distance via Lipschitz test functions. So W1 PQ equals the sup of E of PH minus E sub Q of H. And that's Lipschitz of H, and that is less than or equal to 1. This says basically that the Wasserstein 1 distance between two probability distributions P and Q is the largest difference in expected value they can produce over all one Lipschitz functions H. Two distributions are far apart if some sufficiently smooth payoff function values them very differently. The second equation is the worst case expectation inside the Wasserstein ball. For a Lipschitz objective F, so you have the Lipschitz objective over here, the worst case expected value over all distributions within the radius of epsilon, okay, of the empirical distribution equals the empirical expectation plus the robustness penalty, which is here, the epsilon LF. Distributional uncertainty costs exactly ambiguity radius times the objective sensitivity. And the last equation at the bottom, equation 3, this is the Fournier-Guilin concentration inequality over here. And it makes the ball a genuine confidence set for the unknown law at confidence 1 minus beta over here. Now notice the exponent. The radius shrinks only as the sample size to the lower to the power minus 1 over d. Over here you can see the exponent. Okay, so in high dimension, honest ambiguity contracts very slowly indeed, and no amount of enterprise data rescues it. Finite sample confidence radius epsilon sub n of beta. This gives a data-driven radius for the Wasserstein ambiguity set, with confidence at least 1 minus beta. The true distribution lies within that radius of the empirical distribution. So Wasserstein DRO gives both a robustness penalty and a statistically calibrated ambiguity radius, linking finite data directly to a confidence qualified worst case enterprise decision. Now, moment ambiguity and the saddle. Theorem 11.4. Against K declared moment conditions, the worst case is attained by a distribution on at most K plus 1 points. Theorem 11.5. The game has a saddle point, so the min sup equals sup min, and the robust policy is simply the stochastic optimal policy for one particular worst case law. The worst case expectation operator is monotone, translation equivariant, positively homogeneous, and sub-additive, a coherent risk measure. So let's have a look at the first equation here, moment-based ambiguity set, And you can see P sub MOM here. This defines the set of all probability distributions whose declared moments match the known values M sub j. So over here, M sub j. The support bound that's shown over here says that a worst case distribution can be represented using at most k plus 1 support points. Even though infinitely many distributions may match the moments, the worst case can be represented by only a few scenarios. Now, the second equation is the minimax equality, and under the theorem's conditions, the order of optimization can be reversed without changing the value. The enterprise can choose against the worst distribution, or the adversary can choose a distribution against the best enterprise response, and both lead to the same saddle point value. Okay, so min sup equals sup min. The game does have a saddle point, and so minimizing then maximizing gives the same value as maximizing and then minimizing. The distributionally robust policy is simply the stochastic optimal policy for one particular worst case law, P star. And finally, monotonicity of robust risk. This defines the worst case expectation over an ambiguity set. If the ambiguity set becomes larger, the worst case value can only increase. The more uncertainty distributions you admit as plausible, the more conservative the robust risk measure becomes. The worst case expectation operator is monotone, translation equivariant, positively homogeneous, and sub-additive, which is to say that it is a coherent risk measure. And conversely, every coherent risk measure is a worst case expectation over some set of laws. Chapter 12, Multi-Objective Enterprise Optimization. Theorem 12.1. This characterizes Pareto optimality. A solution is Pareto optimal when no objective can be improved without worsening at least one other objective. In the convex case, Pareto optimal solutions are exactly those selected by suitable non-negative weighted combinations of the objectives. Theorem 12.2, scalarization equivalence, and its scope and condition does matter. Weighted sum scalarization recovers the whole Pareto frontier only under convexity. The epsilon constraint method can recover the entire Pareto frontier by optimizing one objective while imposing minimum acceptable levels on the others. And this equivalence does not require convexity. Theorem 12.3 gives the weighted sum representation. Positive weighted sums always select Pareto optimal solutions, and under convexity, every weakly Pareto optimal point can be obtained this way. Without convexity, some Pareto optimal solutions are invisible to every weighted sum formulation. Theorem 12.4, the enterprise trade-off theorem, where the ratio of weights is the marginal rate of substitution between objectives at the frontier. Along the Pareto frontier, the marginal cost of tightening one objective is exactly its KKT shadow price, so the active multipliers quantify the enterprise's current trade-off rates between competing objectives. Theorem 12.5, Pareto frontier existence theorem. If the feasible set is compact and objectives are continuous, the Pareto frontier is non-empty, and every feasible enterprise proposal is either Pareto efficient or dominated by one that is. Theorem 12.6, enterprise compromise solution theorem. A compromise solution always exists for finite p it is Pareto optimal, and Chebyshev compromise can recover every Pareto optimal solution even without convexity, including frontier points that weighted sums cannot reach. So, on a non-convex enterprise frontier, weighted sums cannot reach the concave portions. Those unreachable regions are real strategies, usually the interesting hybrid ones, and any organization that sets strategy by weighting a scorecard is structurally incapable of selecting them. That is a real result about a real management practice, and it is provable. Chapter 12 is also where the trade-off between growth and margin, or between performance and sustainability, stops being rhetorical and becomes a computed marginal rate of substitution with units. So this chart shows why weighted sum scalarization can miss valid Pareto optimal strategies when the frontier is non-convex. So the gold curve is the true Pareto frontier, while the dashed line shows the points reachable by varying objective weights, and the inward dent that you're showing, this dent, contains efficient solutions that no weighted combination can select. When the Pareto frontier is non-convex, some strategically efficient trade-offs are invisible to any weighted scorecard, even though they are genuinely Pareto optimal. Now, this equation on the right, this says that a point on a Pareto frontier, the slope of the frontier, equals the negative ratio of the objective weights. The ratio W1 to W2 tells us the marginal rate at which the enterprise is willing to trade objective J1 for objective J2 for J1 or J1 for J2 at that efficient point. The negative sign over here, this means improving one objective generally requires giving up some other objective. Now let's turn to the equation over here, Pareto optimization. So here f of x is a vector of enterprise objectives rather than a single scalar objective. The goal is therefore not one unique best point, but the set of Pareto efficient solutions where no objective can be improved without worsening another. Now, Chebyshev compromise formulation, which so that chooses the decision X that minimizes the largest weighted shortfall from a reference or aspiration level R sub j. You can see R sub j over here. And instead of maximizing a weighted average, it minimizes the worst relative disappointment across objectives. So weights that recover a chosen Pareto point, you can see these weights over here. So for a given Pareto optimal point x star, these weights scale each objective according to its distance from the reference point. So Chebyshev scalarization can recover Pareto optimal solutions even on non-convex frontiers, including efficient points that weighted sums may miss. Chapter 13 and 14 are about machine learning for enterprise transformation and AI for enterprise transformation. So let's go over some of the highlights on these two chapters. Theorem 13.1, Enterprise Learning Consistency Theorem. Under standard uniform convergence conditions, empirical risk minimization is statistically consistent. As data grows, the learned enterprise model's true risk converges to the best achievable risk in its hypothesis class. And with increasingly rich classes, can approach Bayes' optimal risk. Theorem 13.2, Generalization Error Theorem. With high probability, a learned enterprise model's true prediction error is bounded by its observed training error, plus a complexity penalty that shrinks as the sample size grows, thereby quantifying the trade-off between model complexity and generalization. Theorem 13.3, enterprise feature representation theorem. Principal component analysis gives the optimal rank R linear representation of enterprise data by retaining the top R covariance eigenvectors, minimizing reconstruction error while making the retained share of variance explicit. Theorem 13.4, enterprise explainability theorem. Shapley values provide the unique attribution of an enterprise prediction that fully allocates the prediction across features while satisfying efficiency, symmetry, zero credit for irrelevant features, and linearity. And theorem 13.5 is about prediction optimization integration. So prediction error translates directly into decision regret. If the objective is Lipschitz in the estimated quantity, then optimization based on an imperfect prediction loses at most 2L times the prediction error. So statistical prediction guarantees become quantitative decision quality guarantees. Theorem 13.6 gives the learning augmented enterprise optimization theorem. As the learned enterprise relationship becomes more accurate with more data, the learning augmented optimization decision converges toward the full information optimum, with decision regret bounded by the underlying prediction error. Now we move to chapter 14, which is about reinforcement learning and artificial intelligence. So theorem 14.1 talks about enterprise value convergence. With bounded rewards and discount factor below 1, the Bellman operators are contractions. So value functions are unique fixed points, value iteration converges geometrically, and a policy greedy with respect to the optimal value function is optimal. Theorem 14.2, enterprise policy improvement theorem. So replacing a policy by one that is greedy with respect to its current value function can only improve enterprise value with equality only at optimality. Thus, policy iteration improves monotonically and on finite state action spaces reaches an optimal policy in finitely many steps. Theorem 14.3. Enterprise reinforcement learning convergence theorem. Under sufficient exploration and standard Robbins-Monroe learning rate conditions, tabular Q-learning converges almost surely to the optimal action value function, so the greedy enterprise policy converges to optimality without requiring a model of the system. Theorem 14.4, knowledge augmented optimization theorem. Knowledge improves optimization by providing a better starting value estimate. The closer the initial estimate is to the true optimum, the fewer contraction iterations are needed to reach a given accuracy. And finally, theorem 14.5, hybrid AI optimization consistency theorem. In a hybrid AI optimization system, AI may propose or accelerate the search, but a sound optimization oracle preserves feasibility and certified optimality, so AI can improve speed without degrading correctness. So we look at the chart here, which shows the central message of theorem 13.5, the model with the lowest prediction error. So here you have prediction error. So here you have prediction error in the horizontal axis. The model with the lowest prediction error is not necessarily the model that produces the best enterprise decision. The horizontal axis measures the prediction error, as I mentioned, while the vertical axis measures the decision regret, the value lost because the decision based on the prediction is not optimal. So the highlighted diamond over here on the left has very low prediction error, but has relatively high regret, while the star over here has higher prediction error compared to the diamond, but a lower, much lower decision regret. Now, the equation at the bottom, the generalization bound. So R of H is less than R hat N of H plus the order of this expression. This says that the model's true risk, R of H, is bounded by the observed empirical risk, Rn of H, plus a complexity penalty. So you have the complexity penalty that shrinks as the sample size n increases. You see n at the bottom here. The term D over here represents model complexity, and delta over here, log 1 over delta, controls the confidence level. A model that fits the data well will also generalize well only if its complexity is justified by the amount of data available. Now, we look at the Shapley attribution, phi of I. The Shapley value averages the feature's marginal contribution over every order in which features could arrive, and is the unique attribution satisfying efficiency, symmetry, null pair, and linearity. Now we move to chapter 15, Enterprise Digital Twins and Autonomous Enterprise Transformation. The twin is the simulator in which policies can be evaluated without being executed. So the architecture closes a loop, and the loop has a known weak link. The framework's autonomy claims are exactly as strong as the twin's extrapolation, and the twin's extrapolation is the thing Volume 1 proved cannot be validated in the region that matters. So the equation at the top in this slide is the Q-learning update rule. So Q sub k plus 1, Q of k of SA is the current estimate of the value of taking action A in state S. So alpha sub k is the learning rate, represented here. R is the immediate reward. R over here is the immediate reward, and the beta is the discount factor. The term this term max beta. So this term actually, yeah. So the term max A prime. Where do we have? Okay, so the term A prime Q sub k S prime A prime. Okay, so this one, when you multiply that, this term is the best estimated future value available from the next state S prime. So S prime is the next state. Q-learning updates the value of a decision by blending the old estimate with what was just learned from the immediate reward, plus the best expected future opportunity. Okay, so this is the immediate reward, the best expected future opportunity. And then these charts here show the extrapolation problem in reinforcement learning. Standard RL convergence requires repeatedly visiting every relevant state, action pair, which a real enterprise cannot do because it experiences only one historical trajectory, whereas a digital twin can simulate many alternative trajectories and provide the repeated exploration needed for learning. So let's look at the Robbins-Monroe learning rate conditions. And we're going to look at this alpha sub SA equals infinity. And then let's see, alpha sub t squared SA, which is finite. So these conditions say the learning rate must decay slowly enough that learning never stops completely, but fast enough that accumulated noise remains finite. Okay? Q-learning must keep updating forever. while gradually reducing the size of each update. Now, on the right side, we see the Bellman optimality operator as a contraction, and H is the Bellman optimality operator, while gamma is less than 1. And that's the discount factor. The inequality over here says that each Bellman update pulls different Q functions closer together. The Bellman operator progressively eliminates error. And finally, Q-learning convergence, Q of t converging to Q star almost surely, under sufficient exploration and the learning rate conditions above, the estimated Q function converges to the optimal Q function Q star with the probability of 1. Persistent exploration plus diminishing learning rates and Bellman contraction make tabular Q-learning converge to the optimal decision values. The final chapter is about, chapter 16 is about enterprise applications and integrated transformation case studies. So declaration, architecture assembly, GEOP instantiation, solution, and readout through the performance and risk layers. The right way to read them is not as validation, n is small, and the outcomes are constructed, but as existence proofs of tractability. They demonstrate that a full enterprise declaration can be carried through the whole apparatus and produce a policy. Now, in this chart, this diagram summarizes the end-to-end DCT workflow. So declare the enterprise attributes, dynamics, and horizon. Assemble the 4 architectures under the compatibility conditions C1 to C5, which we looked at earlier. Instantiate the GEOP with its 5 constraint blocks, which we looked at. Solve it using the strongest optimization method and declaration permits. And then read out performance and risk results with full provenance. The curved arrow back to the beginning over here emphasizes that this is an iterative modeling cycle. Results can force the analyst to revise the declaration and rebuild the model. So this chapter shows that DCT can prove a declared enterprise problem is mathematically tractable and solvable, but those existence results do not validate whether the underlying enterprise model is empirically correct. So the equation, this chain over here, it summarizes the DCT decision pipeline. So we have D, which is the enterprise declaration. We have U sub E, which is the enterprise architecture. Then we have GEOP, the general enterprise optimization problem, instantiated on the unified architecture. And then we have pi star, which is the resulting optimal enterprise policy. And all of this leads to PR, the final performance and risk readouts generated by that policy. So DCT is moving you from a declared model of an enterprise to a unified architecture, and then to a formal optimization problem, onwards to an optimal policy, and finally to auditable performance and risk outcomes. So let me close by giving you the ladder with its concessions, which is what I promised at the start. So when the system is convex, when you made that convexity assumption, that gives us global optimality, computable shadow prices, and there is a cost to it. The cost is an assumption about the enterprise that fails under increasing returns and threshold effects. Nonlinear KKT. That gives us local characterization and sensitivity, but costs us constraint qualification, which fails exactly in distress. Pontryagin gives us costate as the shadow price of state and backward valuation of capability. but it costs us the open loop and needs Mangazarian concavity for sufficiency. Dynamic programming gives us feedback policies and the 2 beta var epsilon divided by 1 minus beta bound that licenses the approximation. But it costs us dimension and error amplification that explodes as beta approaches 1. HJB and verification gives us certification rather than search, but it costs us a PDE nobody will solve exactly in an enterprise dimension. Stochastic HJB gives us option value in the curvature of V, but it costs us identification of sigma. Neurofuzzy gives us a prior on the policy where the dynamics are unidentifiable, but it costs us sample complexity that no theorem here bounds. Distributionally robust assumptions give us distribution-free guarantees, but it costs us conservatism and the choice of var epsilon, which is a judgment. Multi-objective problems gives us computed marginal rates of substitution, but it costs us non-convex frontiers that are unreachable by scalarization. Learning and AI gives us adaptation, but it costs us an exploration requirement the enterprise cannot meet, discharged onto a twin whose fidelity is bounded by a theorem in volume 1. So this chart compares mathematical rigor with enterprise tractability across the major solution methods. The green bars show how strong the formal mathematical guarantees are. The gold bars show how practical the method is for solving realistic enterprise problems at scale. The pattern is clear. Convex optimization and KKT over here, convex optimization and KKT score highly on both rigor and tractability. Pontryagin, dynamic programming, and electively HJB retain strong theory but become much harder to compute as the enterprise model grows. Neurofuzzy methods are comparatively tractable, but provide weaker formal guarantees. Distributionally robust optimization and multi-objective optimization methods sit in the middle. Reinforcement learning over here is flexible, but still has a significant gap between theoretical convergence results and enterprise scale practicability. So the deeper DCT moves into dynamic, stochastic, and policy-based optimization, the larger the gap becomes between what mathematics can prove and what can realistically be computed for a high-dimensional enterprise. At the bottom, we see the equations here. Epsilon L of S is the robustness penalty. 2 beta epsilon divided by 1 minus beta, that is the policy error bound. Then we have the capital pi L sub I, the cumulative transformation sensitivity. And we have the rho of G being less than 1, that's the systematic stability condition. And finally, we have lambda of I, which is the shadow price of constraint I. So basically, what then has DCT actually achieved? It has not produced new optimization mathematics. It also does not claim to do so. What it has done is construct a representation on which the existing mathematics can be turned on an object that previously, and it has been explicit about where that representation is a declaration rather than a discovery. The 3 things I would highlight. First, the monoid structure of transformation, which makes irreversibility algebraic. Second, the 2-number doctrine on resilience, which shows every scalar resilience index is incoherent. And third, the Wasserstein result, which says robustness has a price. And the price is the Lipschitz constant of what you care about. Both equations or objects, let's look at these equations and objects here. The over here, this is the transformation algebra. T being the set of enterprise transformations, the composition of transformations O here, and the identity transformation I, which means transformations form an ordered algebraic system in which actions can be composed sequentially. Now we move to the beta rho hat, which is an element of two-dimensional real space, where beta is the shock absorption capability or capacity, or the resilience margin. And then rho is the recovery rate or persistence parameter. Together, they describe how much disruption the enterprise can withstand and how quickly it recovers. Expectation of P of n of f plus epsilon L of f. This is the expectation of P of n of f is the expected value under the empirical distribution. Epsilon is the ambiguity radius, and L of f is the Lipschitz sensitivity of the objective. So this second term is the price of distributional uncertainty. The viability kernel is represented here, sigma being the feasible enterprise region, and the viab sigma states from which some admissible policy can keep the enterprise feasible indefinitely. So the four objects are transformation structure, resilience profile, distributionally robust value, and sustainable feasible state set. So this brings us to the end of lecture 2 for volume 2. Thanks for watching. Should you have any questions, feel free to contact me. My number is 858-399-1730, and email samir@theregentfinancial.com, or you can also email me at drsamirasif@gmail.com.